Sun is shining, we're in London. I'm with Winfried, who gave the keynote about quantum computing, which is really interesting because we're talking about bits that can be 0 and 1 simultaneously. So we were talking about what you can do with that. So first of all, how do you have a bit that is 1 and 0 at the same time?
So that's a very strange thing about quantum physics. So quantum physics has these weird predictions. For example, something can be at 2 different places at the same time. So you could be sitting here and you can be at home having breakfast all at the same time. In quantum physics, that's actually possible. And with individual atoms, you can actually really observe this. So you can actually see that that happens. And so what we do now is trying to chain these very strange quantum effects to build a new type of technology, quantum computers. And so it's very hard to kind of intuitively see, but it actually really happens. And what we do now is to make use of these quantum effects in order to really make this technology happen.
Okay, so you need to look at the atom level.
Mm-hmm.
And in conventional computing, you have the constraint of Moore's law, which you said to me is ultimately constrained by atoms.
That's right. How small can a transistor really be? That's the question. And it can't be smaller than individual atoms. And so that's where kind of Moore's law more or less will end, when you just can't make things small anymore.
So if with Moore's law, I'm trying to understand this because I'm, as you have gathered, struggling to grasp quantum computing. Because we're looking at harnessing this theoretical property of something being in simultaneous states.
That's right.
In parallel universes?
That's right.
Okay. So we have the constraint of a conventional computer chip, which ultimately comes down to how small can you build a transistor. And then you have your lasers and your electric fields right now, with atoms, trying to harness the effect of an atom being simultaneously in multiple places and turn that into a computer process. That's right.
So quantum computers are very, very strange beasts. They are huge machines. They have nothing to do with a conventional computer. So quantum computers allow you to make use of these quantum effects. How do we do that? We take individual atoms, actually charged atoms, we call them ions, and we hold them in free space using spinning electric fields. And now these electric fields levitate these atoms above a microchip. And now traditionally people use laser beams to implement quantum gates. And the same as classical gates, you do using transistors, quantum gates. People traditionally use laser beams. Now, if you wanted to go to billions of quantum bits, you need billions of pairs of laser beams, all aligned with the accuracy of a hundredths of a millimeter. Now, imagine the engineering required to achieve that kind of thing. So what we have done recently at the University of Sussex is invented a new method where you can take away with all the lasers you previously needed to implement these quantum gates and instead apply voltages to a quantum microchip in order to implement these quantum gates. And because of that, because we simplified this now in such a way, I think it's fair to say that now there's a real perspective to build a large-scale quantum computer. Doesn't make it easy, but it's now possible.
You've simplified the smallest step.
That's right. The most important step we simplified. We took the hardest thing, in my opinion, one of the hardest things we took out of the required engineering and replaced it with something which is inherently much, much simpler.
So now you're a step closer to building your large-scale quantum computers. What can you do with them? What do they allow you that conventional computing doesn't?
So don't think of quantum computers as fast computers. Think of quantum computers as a very, very disruptive technology. A technology which can do certain things you could never dream of before. So you could do things where even the fastest supercomputer in the world right now may take billions of years to calculate a certain problem. A quantum computer could actually calculate it maybe in a day or in a few weeks. So this is why this is so fundamentally different. A quantum computer won't replace conventional computers for all the problems. You have to write quantum algorithms first. So in order to solve a problem with a quantum computer, you need to write first the appropriate quantum algorithm to do so. So there's already quite a number of very, very interesting quantum algorithms out there. And so they allow us to have applications from the financial sector over a whole variety of sectors to science. But the coolest thing for me personally is actually another thing. It's not the existence of these algorithms that I know they're going to change the world and they're going to make a big difference. But the biggest thing for me personally is the fact that quantum physics is the underlying theory which predicts everything around us. So whether the conductivity of a metal, the color of this chair, the process in biology, chemical reactions, that's the theory which actually can explain all of these things. What a quantum computer can do, it actually can properly solve these equations, solve these problems. And by doing so, it's going to completely change science, the way we solve problems. And for me, that's obviously the most exciting thing, because you'll be able to do certain things you could never even dream of doing before.
So one thing that I thought was really interesting that we talked about earlier was you were talking about, so we're going back to the most basic unit, from the possibilities in the financial sector back down to the chip, for want of a better word, the quantum chip. So I found it really interesting that you said you can have, if you have 2 bits, one bit you can be 0 and 1 simultaneously. And with 2 bits you can be 1 and 0, and 0 and 1, and 1 and 1, and 0 and 0.
Exactly.
So do you have a kind of exponential computing power, or is it at the level of randomness?
No, it's an exponential computing power for certain problems. So you have to write an algorithm, and each algorithm will provide a certain speed up. And so fundamentally, I mean, let's start by explaining first how a quantum computer works on a very basic level, because I don't want to immediately just delve right into the technicalities of quantum algorithms. So as you said, like in a classical computer, you have 2 bits, which we have to pick one number and you write it in there. So for example, 0, 1. In a quantum computer, in 2 quantum bits, you can write in 0, 0, 0, 1, 1, 0, 1, 1 all simultaneously. Now, that scales 2 to the power of n. So with 100 quantum bits, you can encode, with 100 classical bits, you can encode 100-bit number, one number.
Yeah.
With 100 quantum bits, you can encode so many numbers. I can actually not say that number. It's such a big number. I cannot say that's a huge number. Just goes as 2 to the power of the number of bits. So many numbers you can encode in a quantum memory. So that's why a quantum computer is fundamentally different to a classical computer. Now you need to use that ability to make some kind of quantum algorithm with it. And the key thing about a quantum computer is that the scaling changes how long a problem takes to solve. Right? Let's factorize 9. Okay. We both can factorize 9. It's 3 times 3, right? You know, that's not very hard. If I were to give you a large number, then not even the fastest supercomputer in the world could factorize that large number. And that's why your credit card details are safe when you put them on the internet, because that's the principle of RSA encoding. That's the difficulty of factorizing a large number makes your credit card details safe when you encrypt them. Now, a quantum computer, because it scales differently, how long it takes to factorize a large number, now suddenly a quantum computer can just break that. Yeah. And that's, in a way, the amazing thing about a quantum computer. And even more so, it doesn't even need a fast clock speed. You know, the clock speed of a quantum computer might be 3 or 4 orders of magnitude slower than of a classical computer. Nevertheless, it can do things a conventional computer may take billions of years to calculate.
Oh, well, that's really exciting. I look forward to seeing what you do next.
Yes, absolutely. It'll be a fun time. So we'll now, in the next 2 years, we are constructing a prototype, which is based on a construction plan we recently published. So that was the very first time somebody said with current technology, we can now build a large-scale quantum computer. And so we've published this, and people are very excited about this, but now we need to actually show that it actually works. So we're building a prototype, and we do that in the next 2 years. And beyond that, we're actually going to build a large-scale quantum computer. So this is going to be a huge machine, and we'll need industry partners for that. And we're looking right now for the right people. And that's going to be a really exciting time, because then we actually be able to solve some of the most interesting problems on the quantum computer.
Work it, make it, do it, makes us